Okay, so recording solution for worksheet 4. So to write this as a piecewise function, you're going to do it like this. You're going to do it like that. That's because if x is bigger than 3, of course this stays as x minus 3. But if x is less than 3, like say 2 or 1 or whatever, then you have to apply a negative to the expression inside the absolute value. This actually simplifies a bit further because you do want simplest terms. And we express it more compactly like this. That'll be 1 and negative 1. That's because these cancel, leaving behind a negative 1. If x is greater than or equal to 3, or if x is less than 3. So it's kind of similar to what we had in the notes not that long ago. Then to write as a piecewise function, then evaluate as x approaches 3, you're going to say it does not exist. That's because your left-hand limit, when you actually take the limit as x approaches 3 from the left of fx, that's going to be negative 1. And your right-hand limit, the limit as x approaches 3 from the right of fx is going to be positive 1. Graphically, we get something like this. So it's very similar to what we did in the notes not that long ago. If I actually pull up those notes. Yeah, we did this a while ago, but in this case we had a shift of 3 right because we did x minus 3 over x minus 3. So, so that's why it does not exist, because your left-hand and right-hand limits don't equal each other as x approaches 3. If we keep moving, see, I already did the sketch for you. There we go. So there's C right there. And then how are they related? It's just a shift of 3 right. So it is a transformation. So hopefully we're okay there with that. Okay, we'll keep moving. For number 2, what you'll want to do is you can try to find the LCD for these two, which is going to be 2x. So multiply this by 2, multiply x and x. So you have 2 minus x over 2x. And down below, you can actually factor as x minus 2 times x plus 2. Then you can flip over the second fraction. And don't forget, you got to keep writing this out. So, and also you can factor out negative from here. So it becomes that. Flip over this, that becomes 1 over x minus 2, x plus 2. And I see a question, we'll get to there in a sec. These cancel. So now I get negative 1 over 2x times x plus 2. If you plug 2 in, you get negative 1 over 4 times 4, and you should get negative 1/16. So that would be the answer for that one there. We have a question. And what's the question about? Okay, so sorry for the late question. but does the greater than or equal to sign in the first one stay there? What happens that both are open? Okay, so great question about the previous question. I'll get there in a sec. So, well, just to recap, number 2, find the LCD, which is 2x for 1 over x and 1 over 2. Combine them like I did here. The bottom we can factor, but write as a fraction, so just put it over 1. Now you're dividing 2 fractions. You flip the second fraction. And also you need to factor a negative from 2 minus x. This little dialog box kind of gives you a hint there to do that. Because if you put the negative back in, that gets you back to 2 minus x, obviously. X minus 2's cancel. Now we have something that we can substitute for x is approaching 2, and we get our limit. So that's the limit for number 2. To address the question about number 1, let me look at that question one more time. Yeah, so usually what's going to happen when you write this as a piecewise function, again, we had this, ultimately a 1 and negative 1. If x is greater than or equal to 3, and if x is less than 3. If I left out that equal sign in the second writing of it, I apologize. So you do need an equal sign somewhere. It doesn't matter where you put it. You do need it somewhere because x, of course, does, we are kind of curious to know that. The one thing actually, oh, actually, never mind. I goofed here. Okay, I see the question now. Actually, the answer should just be this. Sorry, I'm rushing this. You don't put an equal sign for any of these two. My apologies. So do make that correction. I apologize about that. Yeah. Obviously, we can't plug in 3 because it's not going to be defined. So we don't know what y equals at x equals 3. So actually, I was wrong in doing that. I think I just did it by habit because sometimes we do that for piecewise functions, but we can't because x does not equal 3. It would be undefined. So yeah, my apologies about that. There should not be an equal sign for any of these two. And that's just going back to the 2.1 notes. If you were to write this as a piecewise function, does not exist at x equals 0. If I go and clear my screen here. So really, you just write it as 1 and negative 1, x greater than 0, less than 0. In our case, x greater than 3 and x less than 3 for that one. My bad. Now let's look at 3. Again, you can write this as 1 over 1. LCD is going to be x squared. Multiply with that, says 9 minus x squared over x squared. And the bottom can factor out 4, make it x minus 3. And of course, the whole thing's over 1. You flip the second fraction over. Again, the limit as x approaches 3. Three minus x, 3 plus x. And flip that over. And the thing is that you can cross these off, but you do have to leave behind a negative 1 because that's 3 minus x. Remember, 3 minus x is the same thing as negative of x minus 3. And x, so you cross out, but leave behind negative 1. Remember, there's an x squared down here. So you got negative 1, sorry, negative of 3 plus x, my bad, over 4x squared. And that's the limit as x approaches 3. Then you can actually plug in 3. And if you do that, you should get negative 6 up top. And 4 times 36. No, 4 times 9. So you just get 36 on the bottom. So you should get negative 1/6 for number 3. Hopefully that makes sense. I think I did that right. Okay. So that's that one. Number 4. Now here I actually do have solutions. So actually I'm just going to do that for the interest of time. So we go back to this folder. Not quite that one. So let me still do this one by hand. And I think I should have solutions for the other ones. For this one here, actually I did in the video, I believe. You factor out an x on the bottom. And you have sine 6x up top, obviously, as x approaches 0. Now, we did discuss in the 2.1 notes, I don't know why I couldn't, well, whatever. I closed the fill out ones. But we do see that when you have something kind of like this here, sine of 9x over x, that limit's going to be 9. We had that discussion in the video. So if you were to apply that over here, you could break up the fraction as sine 6x over x times 1 over 11x plus 3. You totally can do that. Think about, what if I have like x over 12? Or let's say I have like x cubed over 12. I could write as x times x up top. Down below I could write as like 3 times 2 times 2 if I so desire. So I could write as x over 3 times x over 2 times x over 2. That's totally a fair thing to do. This is the same exact thing as that. So you could totally break up the fractions as a product, as long as things being multiplied together, right? And you factor stuff out. Well, if I take the limit as x approaches 0 of all this, hopefully you recognize that this part right here is just going to be 6. And this part here, if I plug in 0, becomes 1/3. And so multiply that out, you get 2. Also, you can graph this in Desmos. And if you do that, and x is approaching 0, you see it's undefined at 0, but it's getting close to 2 on either side. So Desmos verifies this for us as well. So that's kind of a good thing to do there. Okay, I think now I have solutions for these two. So make sure that's the same thing. Yep. That's the same thing. Yep. Okay. So let's focus on these solutions which are already worked out. Ask questions if you're stuck. Here, notice we broke up this fraction as a minus in between 10x cos x and minus sine 2x. So we break that up as two fractions, which you totally can do. Again, like what if I had like 4 minus 5 over 7? That's totally the same thing as 4 sevenths minus 5 sevenths, right? I could totally get away with that. And then here, I kind of already know that this is going to be 2. I'm just doing kind of something fancy by multiplying top and bottom by 2. I mean, if you do that, then I know this is going to go towards 1. So I still get 2 anyway. And then 10 cosine x, I could plug in 0 for x. And of course, cosine 0 is 1. So 10 minus 2 is 1. Sorry, is 8. But of course, if you substitute right from the get-go, that's a problem because you have 0, 0. That's why you have to resort to some algebraic skills here. For 4, we have a product, so I could break it up as a product of all these. And the way I decided to break it up, 5x squared is 5 times x times x. So you have to get a little creative. You have to be able to see that. Then you realize, well, tan x over x is something I know. Sine 3x over x is something I know. And then e7x over 5, I can just plug in 0 for x and I'm golden. If you do that, this right here is going to be 1/5. Here, that's just 1 as we had in the notes for 2.1. And that's just going to be 3. Again, I got a little creative or a little more formal, I guess. Like if you multiply top and bottom by 3 here, I know this is going to be 1. But honestly, you could just say right from there, just 3, and you're good. So that's the rest of the worksheet. No, it's not an identity. Okay, great question. How do we know about e7x over 5? It's not an identity. I glossed over that. My bad. You just substitute. So that's e to the 0 over 5. Anything to the 0 power you know is 1. That's why you get 1/5. That's all for that one. So if you can substitute after you break up the fractions, please do so. And then you're using your limit properties because all these are being multiplied and you have these individual limits. But the other ones, we're using properties that we discussed in 2.1. And number 3, okay. Oh, this number 3, sorry. I meant number 3 for worksheet 4. Oh, well, there you go. They cancel out, right? Remember, this is my big fraction, which it broke off like this. And then that's totally fair treatment. You totally can do that because you have one denominator. So you can break it off as 2 fractions with the same denominator if there's a minus or plus in between them. And then it's 10x times cos x over x. Of course, these will cancel. That's why you get 10 cos x. And then, of course, you evaluate this limit, evaluate 10 cos x by substituting 0 for x, and you should be okay. Is it always the case that the limit as tan x over x equals 1? Yes, just like sine x over x. So remember our notes over here. Let me clear my screen, clear that. Yes, they'll always equal 1. And that's just something we investigated in the video for the last 2 pages of 2.1. Okay, so that covers the rest of the worksheet. And then the textbook problems. Let's go back to Schoology here. So we had some of these. I put some notes here. 26 to 34 even, obviously graph them, and then find an algebraic, kind of what we did in the notes. 57 through 60 were piecewise functions, I believe, and then there were some multiple choice questions, 7 through 74. So let me pull that up and just, I'll just ask you guys if you have questions. We do need to get the notes started pretty soon for 2.2. But it's good, we need that this discussion anyway. So let me go back. Nope, let's do this. Dropbox. Of course, that's upside down. Let's rotate it. Okay, so 26 to 34 even, were similar to 25 to 33 odd, which you guys had in the previous homework, but in the previous homework, I had you just do these graphically. Here, I want you to do them graphically and solving algebraically. Any of these that you want me to kind of go through to show you how to do it graphically, just plug in Desmos and just trace. That's easy. But any of these that you like me to do algebraically? No? Okay. Here's the other image. I'm here trying to find question. We'll go back to 32, okay? For 32, you break it up like this. Remember, what if I have like 4 plus 5 over like 13? It's the same thing, say 4 13, so it's 5 13s. Because if I saw this originally, I would know to bring those two fractions together. Sometimes we don't break up fractions in this manner, but you can. So you break up like that. What's x over x? That's 1. And of course, the sine x over x. And now I take the limit of those individually. The limit of a constant, so you have the limit as x approaches 0 of 1, plus the limit as x approaches 0 of sine x over x. This is just a constant. We know this. That's just 1. And this right here is from our limit properties from the 2.1 notes. It's also going to be 1. 1 plus 1, of course, is 2. So that's how that one's done. Okay, let's keep moving. So going back here again, you're trying to find RHL and LHLs. RHL is when you're just going from the right side. So obviously when x is slightly bigger than 2 is your RHL. So your RHL right here for 57, limit as x approaches 2 from the right of f of x, which simply means I'm going to focus on this part because obviously x is slightly bigger than 2. So you can plug in 2 straight up, you get 2 over 2 plus 1 into this expression that is associated with that inequality. You get 2. For your LHL, so this is the RHL. For your LHL, which I'll do in blue, obviously you can focus on this part. So like x is a little bit smaller than 2, like maybe 1.9, 1.9999. So you take the limit as x approaches 2 from the left of f of x. So I'm plugging in 2 into 3 minus x. Well, 3 minus 2, of course, is 1. Because these are two different one-sided limits, the limit does not exist as x approaches c, or in this case, as x approaches 2. And that's all you're doing for each of these choices here. You're just simply looking at the left and right-hand limits, see if they are individually, and of course, if they equal each other, yes, the limit exists. If they don't, they don't. And if it does exist, then the actual limit is whatever both the RHL and LHL had equaled. So that's 57 through 60. And then lastly, this one. Rotate, rotate. This does not want to rotate. I don't know why. Let me close that maybe it's just bugging out. Let's try it one more time. No, it doesn't want to open. Okay, let's try it one more time. Okay, that was so weird. Here are just some true or false, or multiple choice questions. Again, if your left and right hand limits are the same thing, of course, limit exists. That's true, definition of limit. 72, you can factor out, you can break up the fractions. We actually just saw that. Number 32, so it's the same thing. And they kind of show you how that's all worked out, which is done really nicely. 73, the answer is C. You're going from one from the left. So obviously you're going to go with this expression right here, 2 minus x, plug in 1, and you get 1. And then as for you to go from the right, you're going to plug in this expression, 1 over 2 is 1/2, 1/2 plus 1 is 3/2, so you get B, 74. So hopefully those aren't too bad. Okay, now let's move on to homework 5. Homework 5, let me click on next. So you had to watch some videos. I broke them into 2 videos. Just so you know, you didn't really have to submit anything. I should probably just turn off the submissions. What you need to do is you need to click on this form and answer the questions in this form. Let's actually take a look at that right now. Let's see how that turned out for you guys. Let me go to my other Google Drive folder. And let's click on that one. And let's look at some of the responses here. So we'll look at the summary. So this way you guys kind of stay anonymous. How do you find horizontal azimuth using the concept of limits? So we are going to get into these notes right now. So 2.2, so make sure you get your notes out because we're going to start that up in just a second. Actually, let's talk about the filled out notes. That might be a little easier right now. So we have this discussion that as x approaches positive or negative infinity, that represents an end behavior asymptote. So you're looking at what happens on the far left and far right of the graph. And we're evaluating this for a lot of different types of functions, especially sine x over x. Now that's a different value, it's 0. And we kind of looked at some things graphically or numerically. We looked at some stuff with limit properties. And we also looked at 1 over x to the n and what happens there, and then some other rational functions. And then we kind of generalized with the degrees, looking at the degree of both numerator and denominator and what generalizations we can make about that. And we also looked at exponential functions as well. So that's basically a recap of all those notes in the video. So looking at your responses, how do you define a horizontal azimuth using the concept of limits? I define a horizontal azimuth as a y value that a function approaches as it is. Good, perfect. This is fantastic. I don't know who wrote this, but whoever did, good job. That's great. Or horizontal azimuth is the behavior of the left and right end of the graph. Yeah, perfect. It's all about behavior and what y is approaching on the left and far left and far right of the graph. Yeah. So it's not a boundary that you can't cross. Good. It's not necessarily a boundary because the graph can cross horizontal, but rather shows which way the graph is going to head towards. Yes. So it looks like you guys are getting this. This is great. It's fantastic. Because if you're not getting it, then I need to discuss that again. Why is it okay to cross horizontal asymptotes? I need to be a little more clear than just saying yes. But yeah, because you describe the end behavior. Ultimately, they're showing what x is approaching in the direction of positive negative infinity. So unless it is crossing out to infinity, then it does not matter if it crosses. That's true. Yeah, they're not strict boundaries. Yes, that's right. Only relates to end behavior. Fantastic. I love being concise. That's really good. Yep, perfect. Why can we have 2 horizontal asymptotes? And by the way, we're going to get into vertical asymptotes in the second half of these notes. If the left and right hand limits approach different numbers, then you have different end behavior. This is a great response right here. They're positive and infinity, so 2 ends of the graph. Yeah, sometimes, I mean, most of the time, the left and right ends will be approaching the same number, but it could be approaching different numbers, as we saw over here. That could happen. We're not gonna have 3 horizontal asymptotes because you only have 2 ends of a graph, right? So that doesn't make any sense. But you could have 2, or a logistic function. A logistic function, I think, kind of look like this. I can't remember exactly, but kind of look like that. And then looking back at the Google document, yes, this should be -2/5. People obviously wrote a little differently, which is fine. But it looks like most of you guys got it. Yeah, the reason why it's -2/5, these are the same. When those are the same, we can generalize that. And a generalization is over here, when m equals n. And analytically, why that happens, if I zoom in just a tad more here, let me clear my screen. You can see that if you multiply both top and bottom of this, by 1 over x4. So you have 2x4 plus x2 over x4, 3x4 plus 1 over x4. If you break up fractions and simplify, you have 2 plus 7 over x, or 3 plus 1 over x4. And these individually each go towards 0, leaving you 2/3, when the limit as x approaches positive infinity is being applied. So that's what's happening there. Okay, so let me go and stop this recording.